what I had introduced earlier. And some people, some of you might directly were asking, why is it that there is strongly correlated systems, DFT doesn't work and all that, right? See, whatever I have given so far was the exact formulation, right? So what I motivated was that we have a non-interacting system, Bohm-Sham system, in which I'm solving this equation. Right? And this gives me the exact density principle. So R is summation I modulus pi I R square. This gives me mu, which is minus I, which is epsilon max by construction, right? And once I know the density, the method of calculating energy is different. The energy in this is written as a function of rho, right? Which is Ts rho. Let me just first write this. Ts rho plus integral T external or rho r Tr plus E Hartley, which is rho r prime over r minus r prime dr prime plus the exchange coordinate. And this Ts rho, because I'm solving Bohm-Sham equation, actually equal to summation over I minus half that is square by I. Right? So having solved this equation, I'm getting everything back. So far I'm not getting any calculation. Right? Now this I can calculate, this I can calculate, this I can calculate. This is the only thing that needs to be approximated. In principle, no matter which Coulombic system or which interacting system I'm talking about, I can do an exact calculation if I do certain things. That should be very clear. It is not DFT does not need to be done. The approximations you make to solve it, that will not be correct. And you have to necessarily approximate. Is that point clear? Because all we have done is rewritten the original many electron problem in terms of this. So what all do I need to do? That's where ingenuity comes in. Right? Question is number one. How to express quantities of interest in terms of this. So all you're doing is writing things in terms of density. All you're getting from the, even if I could solve the Bohm-Sham equation exactly, somehow the rho p and overhead, somewhere, right? I still cannot treat this set of orbitals as a wave function. I think that approximately it may be an orbital, right? So that's one thing. Number two, these are just comments, right? The Bohm-Sham wave function, because it is an interacting, a non-interacting system, is actually this. Y1, in fact, Y1, R1, Y1, R2, so on. I'm not writing this spin part, right? So let me just write this spin part. I'm writing it in this form so that you understand that to indicate that wave function is formed out of these. This is not the exact wave function, it's antisymmetry already, but it is a non-interacting wave function. Whatever quantities I calculate from this approximate, right? It's an approximate wave function. So the only significance of cone sham, so if you compare the right side to this side, is that in cone sham, you get this, nothing else, right? So this is not the system wave function. Okay, that is another thing. Although people use them, but you should be aware if you're doing such a calculation that I'm doing an approximate calculation. Don't be surprised if your results are not matching. Then you won't have to prove it. Okay? So if once you know these limitations, then you know what to expect from the theory and what not to expect. And if you're doing even pushing that calculation, you know what you should do if it's wrong. Number 3. That epsilon unoccupied. Right, so if I solve this, what are you getting? You're getting occupied levels, epsilon max, and then unoccupied levels. Have no meaning. You cannot say, if I take, for example, this gap, this is the exact state energy. If you get it, somewhere something is working. That's where your physical intuition, physics intuition comes in. So keep remembering this whenever you do a calculation. Okay? That is, when you do a calculation, you get a set of numbers. You plot the potential, you plot this and that. Interpret it. Have to be. And if you know these limitations, you know exactly what to think. For example, if you look at the exchange coordination potential, far away goes as -1 over r, that's the finite. Then you know that is the exact potential for an electron far away. Those eigenvalues may be okay. Then I can think of those excited state energies, but again with a pinch of salt. Okay. There is no reason for them. Okay. So epsilon unoccupied have no meaning. Okay. Therefore, if I look at, so I'll keep this exact thing here. If I look at a band, cone sham band, okay. There is epsilon max, okay, EV, EC. This is all right. This is minus I. This has no meaning. I cannot say the delta E equal to E dash. Okay. Then for more reasons than one, there is an exact term that tells you why it cannot be even in the exact system. Okay, I value. Now, a lot of you are in yes.
So, unoccupied no.
Did I make a mistake? Did I make a mistake?
No.
You don't ask a question saying you said. Like I blame you. No. What did I say when I said this? Only epsilon max. So I should say that. And thank you for pointing that out. Epsilon I not equal to max. Occupied. What does the map for me? Okay? Anything else? You said this, and you're right.
I just was wondering because before, these are epsilons are in the previous, I mean, if you do it using the Lagrange multiplier technique, these are just Lagrange multipliers.
That's it.
That's why I was asking.
That's why I said you need ingenuity. Unoccupied highest does have, occupied highest does have. Okay, you wondered properly. Any other comment? Okay, so a lot of you are also, I mean, involved in strongly correlated systems, right? A lot of things Ponsam orbitals are used because we have no other better way of doing it. Again, think because although in principle exact, these are orbitals, right? How do you, sometimes people make from orbitals, they'll make a potential, then they'll make a Q, and that, all that. Are you overcounting? Are you undercounting? All that has to be kept track of. You cannot just say, I'll take the orbital to my calculation. All these inside nitty-gritty details, these things are important. Okay, how do you actually do it? Keep in mind all the time, on track, orbitals do not represent the wave function. Okay, so that is all you can do. Now, let me just talk about some. So I said what they do not do, right? And what you should be doing. For example, expressing everything in terms of density is not easy because what do you do here? In case of wave function, you have an operator for an observable acres. Here's quantity or its expectation value in wave functional theory. Right? Now, in density-based theory, what do I do? I have to write this operator for expectation value as some functional of the density. And this you have to know how to do it. Right? Just to give you an example, suppose you want to calculate the phonon frequency. So you displace slightly from the and then calculate other dot-state energies. Energy is half k square or whatever. That gives you a half omega square and some normal voltage. Right? That you can do. But not every quantity can be expressed in density. How do you do that? So that is where when you're talking about new materials, you're talking about new esoteric materials, you're talking about systems that show different properties, you have to know exactly how to use what you do. Right? And that requires a lot of effort for people who do these calculations. I actually spend time doing that. Okay? That is something you have to know. These are the limitations. I mean, not limitations, it can give you only this much. Right? So, what you do, you're upfront trying to replace an interacting electron followed by a non-interacting one. So, all that transition has to be made properly now. Is that okay? So, keep that in mind. That is one lesson you should really keep in mind. What we have a tendency to do, now that we have a phone channel, run the system, numbers come, and boom, I'm outside. Not. Okay? All right. Now, how do we then go about doing our calculation? So I made these comments. I want to leave them here. Now, this is well known. Here, see. Here. No. And that's where past 50 years, all the efforts have gone. Talk about Van der Waals system, you talk about strongly correlated system, how we make function. That's where the whole game is. It's not DFT that creates the functional. Functional. And although universal, but one doesn't know how to make it. So there are different functions for different systems. Okay? And so some of you who are involved in this calculation, also I would urge you through this workshop, if you can get into exploring these fundamentals to make a good contribution. So this effort, whole material design effort, is actually multi-pronged. People who look at properties of functionals, they make functionals, they look at what's happening, what they make. People who are experts in doing calculations, finding out about the materials, they all have to talk to each other. Everything is important. Computer is your slave. Physical. Don't give it any more value than that. Okay, so now this has to be approximation. How some modern functionals are made how they're tailored towards giving good answers will be covered in the next. Okay, there's the person is someone who has been developing these functions on different systems using different approaches. So that is something you should know how they're developed. Again, once you know how they're developed, you know exactly what their limitations are. That will cover. Right now, I'll just tell you how these calculations are done. Okay, and some functional business and how do they compare with the exact answers. So this is to be solved self-consistently. Okay, again, as I said, I'm focusing on solving the equation as a differential equation. So I'm not talking about basis set. I'm talking about how to solve this. So what you do, you make a grid, right? Make a potential, you solve by numerical techniques, the way eigenvalue problem is solved, shooting method, this method, that method. That again will be done in the tutorial, hands-on. How do you solve Schrodinger equation for simple systems? How do you, do engineering in that? So you should know that also. Because if you solve these on a grid on a simple system, it's very. Okay, now you start with some approximate density, construct your potentials, and just keep running it again and again until you get some sort of a consistency between the potential and the order, right? That's what you do. Now, so simplest approximation is E XC LDA is based on approximate energy per electron by homogeneous electron gas expression. I just want to spend some time on it so that you know exactly where it fits and how to take off. Okay, that's what I'm doing. I mean, all of you must be doing the calculations regularly. My focus is slightly different. Oh, by the way, I mean, now that we did all this, I forgot right on to ask you. After you perform a Kohn-Sham calculation, right? How would you write the Kohn-Sham energy of the system? You understand? Once you understand that Kohn-Sham system is a non-interactive system, I've solved my Kohn-Sham system. What will be the Kohn-Sham? Not a true energy, but Kohn-Sham. Energy for the system. Non-interactive. What would it be? What we do is throw this chalk, where it falls on, that person gets the answer.
Kinetic energy plus the external energy.
Okay, what is that? I don't want to calculate it. I've gotten everything. You answer. So you have to say something. Okay, it hurt, right? 330 review. Both of you, you're discussing.
Yeah, I think that time it gets epsilon I.
Epsilon I, alone. Now I need to discuss. Okay. No, this is simple. This is a non-interacting one. That's it. That's how I know mu is epsilon back. Non-interacting is just you add to the, that's it. No complication anyway, so that's what it is. Now, question is that once you do so, E LDA is equal to integration energy per electron for the density looking at HEG, okay, times the density locally, yeah, okay. Right now I'm just writing, since this LDA depends only on rho. If it was beyond that, I should be taking into account the gradient and everything. Because in this case, what I'm doing is, if there's a density, you just say like this. I'm approximating it like this. At each point, I'm saying some sort of a density there and multiplying the volume on. Right? In principle, I should also take care of this gradient. But in LDA, we don't. We just keep the local density. Is that okay? And EX, you can work out from Hardy's block theory, is minus 3 AF over 4 pi, which is minus 3 over 4 pi, 3 pi square rho locally raised to 1 third. EC, LDA, parameterized based on what they call I usually sort of zero. Okay, so you do that, and then you can write the functional derivative, which is easy to calculate. Take delta EXC delta rho R comes out to be epsilon HC HEG rho R plus epsilon HC HEG 0 in the end. Okay, you do calculations and everything come out to be pretty okay. I mean, within 10% of the system. It's quite surprising how it works, but it works. All right. Now, a few things about it. Number one can show, and the first paper on this was by Kumar, I think 1983. I'm not sure, but that PXC goes as minus 1 over R for finite systems. As R to infinity. And BXC goes as minus 1 over 4Z for, or you can put a epsilon, the direct constant also, semi-infinite systems. So what one is saying is, if there is a finite system, you go far away, it's minus 1 over R. You have a semi-infinite system, you go far away, it's 1 over 4Z or direct constant also, depending on what is. Okay, so it goes like that. However, if you look at LD, and this is one thing that gives you big failure in many, many systems. If I take a finite system or semi-infinite system, it doesn't matter. So there is a finite system. Potential would be, since the system is bound, far away it will go as minus 1 over R, and here would be something. Some potential, right? But here is minus 1 over R. In any finite system, rho as R tends to infinity, C raised to minus some of R. Decrease exponentially, right? So once you calculate this for the exchange goes as rho raised to 1 third, and P correlation goes by constant. if the density is decaying exponentially, rho raised to 1/3 will also decay exponentially, much faster. So inside it may be all right, show the similar behavior. Outside it decays much faster. Okay, this is PFC NDA. If the system, the potential is decaying much faster, right? The true eigenvalue, epsilon max true, which should have been here, gets pushed up. Epsilon max at the end. Because it is less bound. It's not that deep far outside. Is that okay? Right? So epsilon max LDA or smaller necessarily than epsilon max. Does not give you right dimension. I'm pointing out limitations. It may give you density all right. Because far away anyway density doesn't matter. Far away density goes very small. But this is a quantity which you would have liked to see come out properly. It does not come out properly. It's roughly 50% off. Not only that, this potential decays much faster. This has implications. Wherever you're looking for properties that depend on behavior of density far outside, right? It will not come out. I'm trying to tell you what all happens with approximation. Is that okay? For example, another quantity of interest is important for many systems is polarizability. I want to calculate dielectric constants, I want to construct a Green's function, whatever, right? Now, polarizability depends on density outside beacons. So when you apply a field, outside electrons respond to it, and inside is shielded. Is that okay? Now we are talking about regions out here where the density is different from the true density. Polarization abilities are not going to be that accurate. But this is what I mean when I say although numbers come out, you should know how to interpret. So for that, you have to look at these things. Don't just bear out numbers. Look at the potential. Look at the behavior of potential. Tells you. Necessarily. Now, this is based on homogeneous electron gas. That is, all electrons are spread out. They're clean. They're doing everything very nicely, right? Strongly correlated system where they're supposed to keep apart. Okay. LGA, not deep right down. They'll add. Right? People will add U, people, whatever you know. But this is how it works out. Okay, any questions so far? Any comments? So that's why I said the people who do fantastic calculations, they know about particular pull-out things. The people who should be looking at this nitty-gritty also, that teamwork helps getting proper interpretation. Some of you can take up this, some of you can take up the other thing, and then talk. Have respect for it. Any questions, comments? So I'm not focusing on what you did in the calculation, I'm focusing on what all can go wrong. What I'm going to talk about is one reason for failure of this is something called the self-interaction. Self-interaction. Okay, let's talk about that, and that kind of connects across many. There was a, I think it was a X or maybe it was a physics. Okay. You know, the self-interaction correction, the high asymptotic behavior of potential, and there's that problem by rolling and who's the done that? Huh? Kumar. This is a very nice paper. But, they're all related. It's just kind of connects all those things. These are well known in the community. Now, this is how you analyze functions. So the LDA based on local density. And right now, because I can write expression for this, I'll focus on E exchange LDA. Whatever I say goes through for correlation also. I can add correlation in there. Right. So now we look at exchange LDA. Epsilon x is minus 3k over 4 pi, right? Minus 3 over 4 pi, 3 pi squared rho raised to the third. Okay? Now look at hydrogen atom. If I want to do a DFT calculation, I'll do this. That's kinetic energy, external potential, plus integration rho r prime over r minus r prime, dr prime, plus VHC r yi equals right from the DFT point of view, because once I have a density, I should be writing everything. Isn't it? I should be writing Hartley potential, I should be writing exchange coordination potential. But if it is hydrogen atom, can an electron interact with itself? No, it doesn't. Therefore, one property we learn of exchange correlation potential is that for one electron systems, the R3 should be equal to minus or right the other way. That's right. The exchange correlation should be equal to minus VR. Then this will cancel. Right? Similarly, if I were to write the energy for hydrogen atom, it will be phi minus 1 half del square phi minus integration rho r over r dr plus 1 half integration. Just write density anyways. This only phi I r prime r square r minus r prime dr prime plus c. This should be exactly minus of this. But hydrogen atom this clear. So for one electron systems, EXC rho should be equal to minus R. Is that point clear? Because an electron cannot do a self-interact. And now look at LDA. Do you think this can cancel it? I mean, if I take, so now let's see what happens in LDA. This should happen in exchange and exchange correlation both. So now let's see. If I look at Vx for one electron, this will be equal to minus 3 over 2 pi 3 pi square rho raised to 1/3. We are 3. is equal to integration rho r prime over r minus r prime dr prime. Can these two be equal? You like the sign. Is there any reason for them to be equal? Right away you can see no, because far away this would go as exponential. This goes as minus 1 over r, rho r to the 1. So V R 3 plus the LDA not. Similarly, V R 3 plus EXC not equal. If you look at deep into it, what it is doing is saying that LDA, if you make an approximation, you're allowing an electron to interact with itself. Right? That cannot happen. There's something wrong. Right? So this is known as residual. This is known as cell reaction. Whatever this is, electron interact. Right? That's one. And you will find even if I improve the functionals, self-interaction remains. That's a big problem. Self-interaction remains means electron itself is repelling. The system should be confined within this much. It will confine in more space, but electrons are repelling. Each electron is repelling itself in this approximation. It should not fit. Okay, this is one thing that happens. Now this causes those problems that I was talking about. For example, the potential should correct itself, should be minus 1 over r far away. It is not, and if it is not, electron binds itself. Less, other way of looking at it would be electron binds itself less because it is repelling itself. If I repel myself, I'll not be that bound. Right? So, to make something called the self-interaction correction. This is of course very serious. But then, way back in the 83, 84. So what you do, you take a functional, there be a function for n electrons, and for each orbital, you make a self-interaction correction. So this has self-interaction, so I subtract from it I equals 1 to n. E, what is known as LSD, I'm saying LDA, but that's okay. For each phi I, right, plus the heart for each phi I. For each orbital, there should not be any self-interaction, whatever that is, you subtract. By 4. Again, this corrects a lot of problems. Except now there is an I dependence comes in. And there's also a problem with the, the unitarity of the orbitals and all that. But nonetheless, that's the idea that we understand why such a problem comes with this function. And this problem is not restricted to LDA alone. When this is made, it's not through LDA, but something called the local SNBNCBS, which is you make LDA for each. That just keep in mind that is giving you the idea. Okay, so not just LDA, whatever improvement you make, they also have the self-interaction with it. Again, it's not easy. It becomes potential becomes orbital dependent. All right. But this is one major problem. And
It's a corrective system. How can you make this down?
okay. So in developing the functionals, this is what you do. So see, you are making functionals for non-interactive systems, right? You have finite energy. So let me just let me do it. L is D. Local range. Let's see. So for example, I have few upstream electrons and less number of downstream. Right? Let's talk about kinetic energy. What is this? It is y I over I minus r del square y I. Right? Which is summation r. Let's take ms separately. yi ms minus 1/2 del square yi ms. Right? So if I have these orbitals, I'm putting up spin electrons. I'm putting down. I can calculate kinetic energy for this separately, for this separately. When you write from homogeneous electron gas, you can make that process. Similarly, for exchange, exchange is also spin dependent. Because one term is for upspin, one term is for downspin. That expression that I worked out, you can write for upspin plus the downspin. For both, you make the FP. That comes over. So, simply put, this actually comes out to be 1/2 of, or let me put it for exchange, comes out to be 1/2 of EX LDA or rho up twice rho up plus EX LDA twice rho up. This is how it works out. This is just from those equations. It's like this. I have these spins. If I put equal number of down spins, I get the LDA approximation. And I take half it, then add the other. Now for correlation, you make an approximation. For correlation, you don't know how to. Your question is actually correlation, how do you do that? So you make, when you're making an approximation, then I'll approximate it like this. The correlation up and down you can't separate. Up to kinetic and exchange, you can do it. And you say that I'll use the same splitting. Does that answer your question? Yeah. Anything else? Okay. So that's that. So this is the LDA, and this is how a lot of you must be doing these calculations and making an improvement. Right? So we're looking at Ponsam system, and that brings a lot of talk, a lot of functional called hybrid functionals have also come, which makes Hartree-Fock and LDA. How does that come about? So if I look at Ponsam system, it's a non-interacting system, right? It's a non-interacting. And if you look at two systems, there's the true side, right? So what if I take this Ponsam system and I go to two system? Here, if I take interaction to be lambda over r minus r prime, is the BT key, right? Here lambda is 0, lambda is equal to 1, right? So I can go from one system to the other. I have value perturbation theory and value find it. I can say I start from this system, which is E-cone channel at any point along the path, dE by d lambda is equal to whatever that psi lambda is, then the Hamiltonian for that lambda. Psi lambda. Oh. L1 minus here. So by using this perturbation theory, if I switch on the interaction, I can connect from here to here. In this path, what do I do? Both have the same density. Keep. All right. So with this, I can define the exchange correlation energy as follows. H lambda is kinetic energy operator plus V external, which depends on lambda, plus VEE lambda. Why does V external depend on lambda? Because if I want to keep the density fixed, as I change interaction, I have to change external potential also. And VH by d lambda is going to be, this is independent of lambda, plus this we are taking to be like this. This is 1 over r minus 1. So if I do this, delta E, when I go from lambda equal to 0 to lambda equals 1, we're going to integrate psi lambda V external over d lambda plus 1 over r minus r prime psi lambda lambda. Since the density is the same, it comes out to be integrated rho r dv external or d lambda plus psi lambda 1 over r minus r prime psi lambda d lambda. Rho r is the same, so I can integrate this. This comes out to be v external 2 minus v external on champ plus this. So this to define exchange correlation potential, exchange correlation energy, because this delta E is going to be how much? It's going to be summation epsilon I is what the own channel is, right? And the true energy minus this. So through this, you can define actually the exchange correlation function. And then what you do is, instead of doing this from 0 to 1, I can approximate this as 1/2 psi 0, 1 over r minus r prime psi 0 plus psi 1, 1 over r minus r prime psi 1. This is an approximation. Psi 0, as I wrote earlier, is the stated determinant of Poincare particles. Right? So this gives you E RT plus E exchange. This E RT plus E exchange of the true wave function. Right? So this gives you an idea that the true one, I'm throwing out ideas how it can work, right? So from here, first one I can write as 1/2 E exchange RT4, but made from I Ponshan, the psi 0 was Ponshan wave function plus 1/2, so I did approximate E, XC, whatever, LDA. Rho. So I use approximation here. So I'm mixing half of Hartree Fock, half of approximate. Right? This is a hybrid function. This is how it started. The corresponding potential for hybrid functional will be 1/2 B exact, reminded, plus 1/2 B area. Why this thing works is, as you can see, Hartree Fock gave you double band gap. This gave you smaller band gap. Together they become this. Right? Now this was the beginning, and then you could have used different ratios. You could have also used a different kind of hybrid, where what one did was we split the Coulomb potential, right? 1 over r minus r prime. So you could some V short range will be like E raised to minus lambda r over r plus V long range. Short range, you use the approximation, long range, you use Hartree Fock. Okay, so these are now, as I said earlier, these are different techniques that you can use. Now, how do knowing exact answers come in handy? How do I fix this parameter? So I can even write this as sum alpha 1 minus alpha. Here there is this lambda. How do I fix this? Right? I'm just giving you trying showing these ideas. So how do I?
One question.
One second. Yes.
So the lambda in the exponential has nothing to do with the lambda in the interpolation parameter, right?
So that again?
Lambda in the exponential
Yes.
has nothing to do with the interpolation parameter you
No. So I can write this as alpha. Yeah. I'm sorry. Yeah. And this is some parameter. This is not that lambda.
you use alpha.
Yeah. So I'm using alpha. So all I'm doing is this was this potential. I'm removing. I'm splitting it into this part and this part. There's some parameter. All right. So this part short range is e raised to minus alpha r over r. This one. Now, how do I fix? This is one big group in Israel that actually came up with this idea how to fix lambda and alpha. That's alpha, right? The Leo Economics group. And what they do is they calculate the expectation that the energy functional energy. You know, this phi I, E, phi I plus all that. Plus E hybrid. Okay? And once you do that, I can calculate the ionization energy as E n minus 1 minus E. Now I'm also getting mu equals minus I is equals epsilon max. They fit this parameter until these two match. Is the idea clear? I'm doing a Ponshan calculation. Got this epsilon max is supposed to be the ionization potential. Theoretically, I'm also calculating ionization potential by calculating the energy difference. Use the same function and keep varying it until these two match. That's one way of fixing it. And they get beautiful spectroscopic. Right? So these are different ideas that are working on this side. Okay? Any questions? And then you can make double hybrid, more hybrid, and all that. That becomes the basic. Yeah.
There will be relation between alpha and this
to the lambda.
Well, I mean, that's what he said. This is alpha. I put this alpha. One parameter. Right? Okay, so this is Onsham using functionals. Now, how to create these functionals? What all is done will be talked about by Professor Prasanjit Samal. Next step. He has been developing these functionals. Okay, so this is the whole idea. That you create these functions and you want to talk about all this stuff. That's really developing functions is an art as well as science. You will take care of, satisfying as many exact properties as possible. So you have no exact properties, that's why you investigate these functions. And so, for example, one function which is becoming very popular now is scan function by Purdue has 17 properties that you satisfy exact properties. Okay, I don't know how many properties you satisfy you. We'll be doing land structures, things like that. Okay, so that's about that. Now, finally, in this, how much time do I have left now? Thank you. Yeah, don't worry. Okay, now one topic which is also of a lot of interest and it has implications for many things is the derivative discontinuity. This is the next thing. I'll come to that, but before that, I just want to maybe I can go now. So let's talk about this. I told you that mu by construction is minus I, right? Suppose I have a system, on-champ system, which I'm solving. Minus 1 upper square plus the external plus part the exchange for this acting on y r. So y of it's not max is equal to minus. Suppose I go to the next property. So suppose this n electron system. Okay, this is n electrons. This is minus. If you just keep it 1 plus 2 plus 1. Okay. Now, and then infinite number of electrons. Now I change it to add one more electron. So let's say this is n and this is n plus 1. There's an empty space here, so for ground state will go here, right? Suddenly, mu changes. So minus I changes to let's say affinity. Ionization potential of n plus 1 electron system is the affinity for the n electron system. So this is affinity of n electron system. I electron system. And I is always greater than this. You check the periodic table. So what happened? I had 10 raised to 23 electrons. Adding one more electron, should that change anything, right? 1 in 10 raised to 23, right? But this ionization energy is epsilon max. So minus I suddenly went up to if so even one electron was added to make it more dramatic. Let's write in U to be a cube. And this can the Hartley potential change? To add to 10 raised to 29 electrons, one more electron. So Hartley potential change? No. All you've done is added 10 raised to minus 29. Everything, so if Hartley potential doesn't change, external potential remains the same. How could this jump come along? Only thing that can change should jump out. This implies PXC changes by constant. So I think that's changed. This is the price you pay for trying to represent an interacting system by a non-interacting. Okay. Now there's another way of looking at it. The other way, because they are all related. So you can show that the density for a finite system as r goes to infinity goes as e raised to minus 2 square root of minus 2r. Okay. Now I have a finite system. There is a potential, and the density out here goes exact density 2 square root of minus 2r. An electron. Okay. So if you calculate far away, external potential goes to 0. External plus hardly go to 0. All you have is this. So V external plus V hardly go to 0. So you can write, calculate this, PXC comes out to be constant equals I, right? PXC to be equal to some mu minus 1/2 L square whatever. So the constant you can remove. You add mu to make it PXC going to 0. Do this calculation and you'll find if you just take L square row by row, there are two i's. You have to add a constant to make it come to 0. That constant is mu. If you take an n plus 1 electron system, right, density will go as minus 2 square root of minus 2a. So you have to shift potential by a. Two cases. The shifting inside the density remains the same because you are adding a very small number of electrons. So here it has to shift by different amounts. That means another way of doing it. Okay. Work it out easily. Just, I'm just giving you the ideas. Now, where all it comes from rigorously is that to DFT for on the number of electrons. DFT for non-integer number of electrons. So what first thing you will ask, why, how can you do it? See, after all, I have a functional row. I can put in any row out here. Whether it integrates to n, integrates to n plus 0.5, and what do I get? For non-integer electrons, it is written as n minus f n minus f row of n plus f rho plus 1 is the density. Ensure that it mixes two densities in this manner, if you want to write, and the energy comes out to be n minus m plus m plus 1 for n plus 1 every. Let's show this, and this was done by Purdue, R, DV, and Martin. I think in 1980. Yeah. If energy is like that, it's not E versus N, becomes electric segment supply. This is E N minus 1, E N, E N. This curve is there. If this is corrected segment, mu out here will be minus I, mu out here minus A. If you do the statistical mixing of densities, you can do DFT for non-integer number of electrons, and then you can show rigorously that you jumps as you cross an integer number of electrons. This is precisely what I was motivating earlier.
In the last expression for n minus a times.
This will be here. Okay. Okay. So what I was showing you just heuristically can actually be cool. And this shows you that exchange correlation actually jumps. Those of us who generate exact potentials actually it's shown by doing so. And that has implications. Just give you one and then I'll stop. For example, if you take the band gap problem, even if you're doing it exactly, so I have the EV, EC, and this is minus I. When you do band gap problem, what do you want to calculate? You want to add one electron and find out how much is the energy difference. Usually, this is what you call E gap or trap, right? If I add one more electron plus one electron, what happens? This potential is jumping up. So this whole thing is shaped up by this delta, which is I minus A. Actual gap is actually this E mod I minus A. Actual gap is going to be more than the function gap. The result of the exchange correlation. And this has other implications in terms of step structure between molecules, molecule transistors and all that, to stretch a molecule. All these jumps are shown there. So I think I'll stop here. I'll give you an overview of what the exact properties are. How do you do function-based calculations? Later. So do follow these out. These have the effect results of the calculations whether we make an approximation. Whether we are violating one of these exact results, you are making an approximation and the results should be looked at that time. Okay, thank you very much.
Can I make a comment
Yeah.
before questions are asked? Is that good to point out for the students that there are no self interactions in the function.
Yeah. Right. Yeah, sure. RT block has no self-interaction. That cancels exactly. But if you add the self-interaction term, in the case you from the function.
Any other?
Okay. Any questions from that side?
Yeah, online people. Online people, you can unmute and ask the question, please. You can hear us?
Hello, sir.
Yeah, please go ahead.
So, sir, thank you for the lecture. I have one question regarding the hybrid functionals that you are talking.
You have to be a bit louder.
Hello, am I audible?
Yes, yes.
So, for the hybrid functionals, when it actually works, then the accuracy for these functionals must give the more accurate results than LDA, right?
Yes.
So, sir, how does the mixing that you have shown here? So, how it actually controls, or is there any fixed ratio of the Hartree fog and the exchange correlation part that makes this hybrid?
Yes, I talked about that. One way is to use the exact ionization potential theorem, and this is how this Cronix group has been doing it. That you satisfy, you change, you fix your parameters until the energy difference and the ionization potential from the orbital come out to be the same.
So that being said, it's changeable, right? So we can change to vary it to get certain results to system to
Yes.
system.
Yes. You're tuning the functions for a system, yes.
Okay, sir, got it. Thank you.
Using a certain property. A certain exact property. Does that answer your question?
Yes, sir. Thank you.